Complex numbers. Hello, welcome to this session, a session that is going to talk about complex numbers. Now, for this particular topic, we are going to look at it in three phases. The first one shall be complex numbers to a certain level, then we'll do the second and the third tutorial, simply because I cannot have them in the same tutorial. Purposely, people ask, what are complex numbers? A complex number mathematically is any figure that can be written or that is written in a form a plus bi all x plus iy. When you find such numbers, these are called complex numbers. You don't need to stress. You know, with mathematics, we enjoy as we learn. Now, when you have this, a complex numbers have the real part. A real part of a complex number is the one without I, because I stands for imaginary. When you look at x plus iy, in this sense, the iy becomes the imaginary part and x becomes the real part. This one is a is becoming the real part and b, I becomes the imaginary part. Now, look at this part. Let's briefly look at this. Practically, if you had, they give you this piece of chalk and you throw it up, can you have another piece of chalk and throw it where the other one stopped? If at all there was no boundaries, leave alone throwing it and touches the top of the roof. No, but throwing it and stopping in the middle, then it comes back. Can you be able to tell me where it stopped? If your answer is no, so you can just imagine how much it went. That's why this one is normally called the imaginary axis, which we call the y-axis. We call it the imaginary axis because distances here sometimes, or in most cases, if not all times, are imaginary. But horizontally, if I moved from here to here, if I was moving from where I'm standing up to maybe this line, I will say 1, 2, 3, 4 steps. Then I will come back. That one is too real and I can calculate. That's why this one is normally called the real axis, the x-axis. And that's why for these particular ones, the first figure as we write, we take it the real value and normally denoted on the x-axis, and the imaginary value normally takes up the vertical axis simply because vertical movements in most cases are imaginary movements. Having heard from that, come back to this. There are two things that you should know as well before we move on with these complex numbers. There are numbers that are purely imaginary, and there are numbers that are purely real. When do we talk about a purely real complex number? A purely real number is the one where the imaginary part is 0. Just assume if b was 0, this would be a. So a becomes purely real. Why? Because its imaginary part is 0. And when we look at this, if the x value is 0 and you have y, we say this one is purely imaginary simply because its real part is 0. So we have purely imaginary numbers and purely real numbers. There's another question sometimes that moves where someone said, if someone wrote 4, 5, or 6, and someone asks, are these complex numbers? I would say yes. All real numbers, I repeat, all real numbers are complex numbers whose imaginary parts are 0. So someone can challenge you and say, no, this is 4 plus 0i. So only that this is a purely real, purely real, but this does not take away the fact that they would be complex numbers had their imaginary parts not been 0. Now, after having listened to that, let us talk about the arithmetic. We are now going to talk about the addition, subtraction, multiplication, and division of complex numbers. Let us start with addition. Addition of complex numbers. Now, before adding complex numbers, ask yourself, why is it that we have I on this. How do we equate I? How do we normally realize that a complex number, all I, equates to a certain value? Now, mathematicians sat. In fact, this will confuse you. Let me first remove this. And I settle that. So I, as in I, the imaginary part, always is equal to negative 1, such that, remember, at some levels, especially ordinary levels, we normally don't have square roots of negative numbers. And when you press this on a calculator, it will not give you the answer direct. However, we normally say I equals square root of negative 1. Why? By convention. Mathematicians sat later, way back, and realized that to make it simple for people to solve very, very big expressions, they should find out the solutions to the square root of negative. And they said, since you cannot get a real value, let us say this is an imaginary answer. So the imaginary answer is always equal to the square root of negative 1. And that's why if someone has I equals square root of negative 4, this, we normally say if A equals square root of negative 4, we shall say A shall be square root of negative 1 times square root of 4, such that the square root of negative 1 reflects this I. And that's what the root of 4 we all know. It is plus or minus 1. That's when you have plus or minus 2 I. This I representing square root of negative 1. So after having I as this, now the question will come back. How do we extend with i's? So when you square both sides, I equals square root of negative 1. If you square this side and square this side, this square will cancel with this root because root means power negative. Sorry, means power a half. So we shall have I squared as negative 1. As negative 1. This should sink deep into your mind that wherever you have I squared is always negative 1. When you come here, shortly here, from I squared equals negative 1. So we said I equals square root of negative 1. Now we are having I squared as negative 1, just like we've seen after squaring both sides. Now, what if we have I cubed? Now, I cubed will imply you are having I squared times I. That will be the implication. So I cubed, you get I squared times I. So you get I power 4. I power 4 will mean you have I squared, because we ask you what is I cubed when you get I cubed. So you get I squared times I. An implication, I squared is negative 1, is I squared times I, whereby I squared is negative 1, then multiply by I, so which is negative I. I cubed equals negative I. How does it become? I squared being negative 1, get negative 1 times I to get negative I. Look at this, I power 4. I power 4 means you have I squared times I squared, giving you negative 1 times negative 1, which gives you a 1. So you realized I power 5, I power 6. This is for you to try. I power 5. I power 5 will mean I power 4 times I. And I power 4 is clear this. And question, I power 5 will be positive I. You should make sure that you calculate this work and understand it. Let this mathematics sink into your blood and you breathe it. So don't force such stuff to go away easily. So when you have this, you can have I5, I power 6 is I cubed times I cubed. So negative 1 times negative I. Realize you get your answer here. So you complete this. After having this and knowing all this, now let us see the arithmetic or the algebra. So we have addition, of complex numbers. My brothers and sisters, if we are adding, or as we're adding these complex numbers, what we practically do is You do like what you do in vectors. You remember what you did in vectors? Consider the following complex numbers. Part A, x plus iy, and part B, a plus ib. If I had these two. If I'm having these two complex numbers, then someone said, question, find. If I use a plus bi here and yet I have a b, it may disturb. Let me pick another one, which is maybe c plus di, such that I don't confuse the letters a and b. So if we have find a plus b, if we are adding complex numbers, what we do, you add real part to a real part, and then an imaginary part to an imaginary part. Just like you're adding I to I component and J to J component and K to K component. So we shall have in the solution, A plus B shall be the same as A is X plus IY. So it is X plus IY plus B, which is C plus DI. Now, when you look at this is a real part, this is a real part. This is an imaginary part, and we've said if we are adding complex numbers, add real to real, imaginary to imaginary. So what you do now, correct like terms. So we shall have X plus C plus IY plus DI. When you look at this, these are real parts. And I being common on this, factorize it out and have y dip. So we shall have x plus c plus y plus d I. Therefore, a plus b shall practically equal to that. So in that sense, you say you can add complex numbers. If you have a practical example, so practical. This is a practical question. Given that z equals 3 plus 2i and m equals 5 plus I. If z, let us not go this way. Let's just say m equals by 5i. Find part A, z plus m, and part B, m plus z shall be the same. Let's just have z plus m. If you're adding this, kindly help me do this. Should I do it? I thought you would do this one. Okay, let me do this. Then subsequently, we shall have ours to try. So when you have z plus m, we shall have in the solution, z plus m shall be the same as, the value of z is 3 plus 2i. 3 plus 2i. Then plus m, the value of m is 5 plus I. So we shall have 5 plus I. When you look at this, remember we said, wherever you find I, that's an imaginary part. When you find a number that does not have any part that is I, we call that one the real part of a complex number. So a 3 plus a 5, 3 plus 5 being real to reflect this. Now plus a 2 plus 5, we factorize out I to reflect this now. 2 plus 5 into I. When you add the 2, let me put this one here. If you add 3 plus 5, you end up getting 8. And 2 plus 5, you get up getting, say, 7i. So this would be the answer for z plus m. If z and m are complex numbers, that is totally for addition. Now, subtraction. Now, for complex numbers, subtraction is exactly having the same mindset or the same methodology like addition. So the way you do the subtraction, the same way we did the addition. So what we do for this case, I'm going to give two complex numbers. We are using the very same process, and you help me do that. Because what we've done here, just if this was a negative, do the needful and do the subtraction. Because they need the same method. So just allow me to put their question. Try it, please. Given that a complex number z equals to maybe 5 plus 3i, and given complex numbers, let us have a pair. Given complex numbers, z equals that, and m equals maybe 7 plus 5i. Someone says, find part A, z minus m, and part B, m minus z. If you have those two questions about that, okay, allow me do one of the two. I'm doing the simpler one because I want you to do the harder one as well. So when you have this, in your solution, you are going to say, let me opt for part B, m minus z. M minus z, this is part B, shall equal to, the value of m is 7 plus 5i. 7 plus 5i minus, remember we are subtracting. And the moment you're subtracting, be careful with complex numbers. If a complex number was given as a pair of a real and an imaginary part, put them in a bracket wherever you're subtracting them. So minus 5 plus 3i. Why do we subtract? Simply because this negative affects both of them. If you don't subtract, the negative is going to affect only the first figure and the second one shall remain positive. In that sense, you're going to lose it. So what we do here, we as well subtract real, imaginary, imaginary. So we shall have 7 minus 5 plus 5i minus 3i. So that we have a 2 plus 5i minus 3i, you get a 2i, which is the same as 2 into 1 plus i. No, but what if I leave it this way? It is okay. I just wanted to do it mathematically thoroughly well. That's what I did. But it's okay. Now, for z minus m, you can do multiplication and division of complex numbers. Let me minimize some space here. Multiplication and division of complex numbers. Now, if when we are multiplying complex numbers, we are having two complex numbers, say, if z equals x plus iy, and say the complex conjugate equals x minus iy. Something I had not said. When you look at these two complex numbers, if a complex number is z, its conjugate, a conjugate is the same complex number, we just change the sign in between. If the complex number was 2 plus 3i, and this one was z as a complex number, if you put z star, some people put this, and commonly is this. This one means the complex conjugate of this, and the complex conjugate It is the very same complex number given to you, but change the sign in between the real value and the imaginary value. If this was positive, this conjugate becomes negative. If this was negative, its conjugate becomes positive. Thank you. Now, when you look at this, z equals x plus iy, and its conjugate automatically becomes x minus iy. If someone said, find z times its conjugate. Now, if you are having this, don't stress, my brother. What you do, you tell us that in our solution, z times the complex conjugate of z shall be, it is x plus iy times x minus iy. For multiplication, the most important thing is knowing the way how these i's are going to change. You come back to what we said as we were starting, that when you multiply I, when you square I, you get -1. When you cube I, you get -I. You must come back to this, such that wherever you find I squared, you know what to put there. So, back to the point. So, for this one, we multiply normally. We don't do like addition and subtraction. We multiply normal multiplication. Now, in normal multiplication, you are going to have x times this bracket and iy times this same times that same bracket. Now, this one will imply x times, it is x into x minus iy. Remember, this x has multiplied this. This is a positive thing. So, plus iy into x minus iy. Or some other people may do it directly, x times x times this. But this one is a little cheaper to understand. Now, when you look at this, x times x becomes x squared. Then x times iy, you get minus x iy. Now, plus, look at this. It is iy times x, which is x iy. Then iy times iy. Remember, I is multiplying I, so it is becoming I squared. Let me first leave it as an x. Minus I squared, because I is multiplying I and y is multiplying y, so y is also squared. Y is also squared. Since these ones are squared, hope you can see this clearly. I've left the negative simply because I want us to first agree with this. But we say that first that I squared is always -1. Right from this, square root of -1 equals I. When you square both sides, you end up that I squared shall equal to -1. After realizing that, then do the needful. We shall have x squared minus x. Now, xiy plus xiy, this one will cancel out. So this one becomes 0. So it is x squared minus, now, minus I squared, but remember this I squared is -1 now. So minus -1 y squared. That's why this one cancels, this will become positive, and you end up having x squared plus y squared. If at all we are multiplying the two. So with multiplication, the most important part is knowing how to juggle the i's and normal multiplication, like the matrix multiplication. The multiplication that you did previously is the multiplication that we do now. The only difference is, for this, we have I, which I is changing depending on whether it is a cube, a square, or a